Hello, students. We're going to work on a little lesson today on inverse functions. This is kind of a bridge lesson between logarithms and exponential functions. There are just a few things I want to remind you about inverses, and then we'll do some calculus with those. So first of all, you can show that two functions are inverses if uh, when you plug in one function into the other, that it undoes itself and you get x. And then I've got some properties that I've listed for you. And probably the biggest pair would be 2 and 3, that the domains and ranges change places, and that can be seen in the form of an ordered pair, that if F contains the ordered pair AB, then F inverse, which note that notation, it's F and it looks like an exponent of -1, but you read it F inverse, contains the order pair BA. So the X and Y trade places. As far as the calculus is concerned, that has to do with showing that an inverse function exists. So a function will have an inverse if and only if that function is 1-to-1, which means that for each x, there's only one y. So in other words, the y cannot repeat. So there are a couple of tests that you could perform. One would be through calculus, showing by doing the derivative and then looking to see whether the function is always increasing or always decreasing, and therefore strictly monotonic. If that is the case, then the function's 1-to-1 and therefore has an inverse. There is also the horizontal line test, similar to the vertical line test for whether something is a function. The horizontal line test says that if a horizontal line intersects a graph at most once, then the function has an inverse. So I'm going to have us just look at a few types of things that you can do with calculus that involve inverses. One of them is to determine if the function has an inverse. So in this first problem, we're going to find the derivative, and I chose something pretty simple to do the derivative of. So f prime of x would equal -1 minus 3x to the second power. And then we'll use that to set that equal to 0. And so f prime of x, setting that equal to 0, will give us the critical numbers. So -1 minus 3x to the second equals 0. We can add 1 and divide by -3. So adding 1 and dividing by -3, we get -1/3. And so when we take the square root of each side, we end up getting a non-real number. So x squared can't equal -1/3, and therefore there are no critical numbers. So no critical numbers. And so you can set up a chart. So now you're doing your analysis. Well, we'll do the interval first, just to remind you what these charts look like. So you'll have your interval. You'll look at f prime and then what's going on with f. And because there is only one interval, since there are not any critical numbers, then we don't need a very big table. Try to make my lines a little bit straighter, but that's all right. So we're going from negative infinity to infinity because we did not have any critical numbers. So if we plug in any number, such as 0, we get negative 1 minus 3 times 0. So we know that f prime is going to be negative for all the real numbers, and therefore it is always decreasing. And so because it didn't have any critical numbers, when you analyze the function, we find out that f is monotonic, decreasing, which means that, so we'll say therefore f is 1 to 1, and your conclusion is that f has an inverse. So it doesn't ask us to find that inverse, just to show or determine if f does have an inverse. Now, if we had critical numbers, we would have more rows in the table. And if you find that f changes from decreasing to increasing or vice versa, then f is not 1 to 1 and would not have an inverse. So that's one way that you could be asked to use calculus in determining whether or not you have a function. Now, the next theorem that we're going to work with is the derivative of an inverse function. And we will use this theorem. It's a little unusual, but we will use this theorem when finding an inverse is difficult or impossible. So I chose a little bit more of a difficult problem to illustrate this with, because I am not able, you are not able to switch the x and y and solve this one for the y. So we would be, if we needed to find the derivative at a certain value, we would need to use this theorem. So I'll show you a third example later on where we are easily able to do the inverse first and then do the derivative. So I've given you 5 steps, and as I go through this problem, I'm going to go through it numbering those steps for you. So step number 1 says to set f of x equal to a. So this is the x value of our inverse, and we're going to want to find the y value that goes with that. So we'll first do f of x and set that equal to a. That's what we're going to start with. So 1/27 times x to the 5th plus 2x to the 3rd power. We'll set that equal to negative 11. And so I can multiply both sides by 27. That will give me x to the 5th plus 2x to the 3rd equals negative, and that is 297. And then I'll add that to both sides to get my equation equal to 0. And I certainly don't want to factor that. So we're going to go to Desmos, and I already have this typed in for us. We're looking for the x-intercept, and it's at -3. So our x equals -3. And again, that was typing in the y equals x to the 5th plus 2x to the 3rd plus 297. We get it crossing the x-axis at -3. So we'll have x equaling -3. Now that's step 1. Step number 2, which is completely related to that, is to write your ordered pair for f. So for f, we have -3, -11. So this is for f. Now, for f inverse, we trade the x and the y. So this is for f inverse. And then step 4, I want you to find, f prime of x. Now, that's not as hard as it may look to do. So f prime, now remember f prime, we're working with this version right here, so we'll have the 1/27th as the coefficient, and then it was x to the 5th, so that will become 5x to the 4th plus, and then we'll bring the 3 times the 2 and have 6x to the 2nd. And so that's f prime. And then step 5 is actually where we use the theorem. So for step number 5, it says that f inverse, so I'm going to write what we're finding, f inverse prime of x. Now, the x that we're using is this -11. That is equal to 1 over, all right, f prime of f inverse of -11. Now that looks like that's a really difficult thing, but it isn't. You just have to get used to the symbols. So this is really 1 over f prime of, and then f inverse of -11. This is why I had you do step 3. F inverse of -11 is just this y value, this ordered pair. So you can see why we had to do this work. We had to find what would trade places in this ordered pair so that we would know this y value. So we're really doing 1 over f prime of -3. Now once you're here, then it's just a matter of plugging in -3 into f prime. So that would be 1 over, and we're going to use a calculator after this step. So 1 over 1/27th times, and then 5 times -3 to the 4th plus 6 times -3 to the 2nd. And again, I didn't want to do that calculation, so I used Desmos. I typed it in. I only typed in the denominator. So it's this line right here, and unbelievably, that equals 17. So the answer for this problem is 1 over 17. I think I'm going to actually put that up here at the top. So 1 over 17 would be that final answer for f inverse prime of -11. Okay, so I'll draw an arrow up there so that you can see what I did. So again, you would use this process to find the derivative of the inverse of a particular number when it's not possible to actually find the inverse of the function. So you wouldn't even be able to use your calculator because you can't find the inverse of the function. So you wouldn't be able to find the inverse first and then do its derivative. So this is a process for kind of going about finding the derivative in a roundabout way. All right, and then the third thing that inverses have to do with calculus would be to verify reciprocal slopes at where the inverses have the opposite ordered pairs. So I've got for your third example a problem, f of x equals x to the third. And for part A, we are going to find the inverse of that function. And I'm having you state the domains just to remind yourself as you do your homework that if you have square roots or if you have fractions, to be aware of places where that domain may not be defined. So for part A of this problem, we have f of x equaling x to the third. So as you're working with inverses, the first thing to do is to write it as y equals x to the third. Then as you find the inverse, so I'm going to change colors because these are not equivalent lines. Then you would switch the x and the y, and then you solve it for y. So we would need to take the third root of each side. So the third root of x would equal y, and then we'll relabel that as f inverse of x. So f inverse of x is the third root of x. And then we'll look at their domains. So the domain on each one of these is just negative infinity to infinity. So, whoops, I meant to change colors there. So nothing unusual about these domains, but just be aware of this as you work with inverses, especially like squares and square roots. So both domains, negative infinity to infinity. All right, part B. Given the ordered pair AB, state the corresponding ordered pair on the graph of F inverse. So that's easy for part B. The ordered pair would just trade places. So 1/8, 1/2. And then the last part, part C, I think I'll put it right here to start. For part C, we're going to show that the slopes of F and F inverse are reciprocals at the given points. So since we were able to find the inverse, we can just do both derivatives without having to use the theorem that we used in the previous problem. So I'll start with f of x and go to f prime of x. So f prime of x is equal to 3x to the second, and the given ordered pair, the x is 1/2. So f prime of 1/2 would be 3 times 1/2 squared, and that's going to equal 3/4. So there's our first function and its derivative. So now we're going to look at f inverse prime, and it's just a little bit longer, so I'm going to start up here. So f inverse prime of x would equal, all right, now if we think of this as x to the 1/3 power, then that would be 1/3 x to the negative 2/3 power. And since I'm going to be substituting in a number, I'm going to rewrite that as 1 over 3 times the third root of x to the second. And so we have to do f inverse prime of, and then for this one, the x is 1/8. F inverse prime of 1/8. Again, I do not need to do the theorem that we used up above because I was already able to find the inverse and do its derivative. I'm just going to plug in the 1/8 into this derivative. So that would be 1 over 3, and then I'm doing the third root of 1/8 squared. Now that may seem a little intimidating, but it's really not. So that's 1 over 3, and then I'm going to do the third root last. I'm going to do the 1/8 squared first. So that's 1/64th, and the third root of that is 1/4. So this is really 1 over 3 times a fourth, or 3/4. Well, those are reciprocals. We would probably write it as 4/3. So these two slopes, because remember your derivative is your slope, these two slopes are reciprocals, and I'll make that statement. The slopes are the derivatives are reciprocals. At A, B, and B, A. So this is what you were asked to find. Let me fix that real quickly. And that would be the conclusion that you would make for this type of problem. So there will be some problems that might involve logarithms, but I wanted to try to describe the different uses of the derivative with inverses using functions that you are maybe a little more familiar with. Again, this is more of a bridge lesson than anything. So I do not have a very long assignment for it, and let me know if you have any questions.